Hello. Okay, so the purpose of this video is to basically describe how exponential functions can be shifted. Okay, so recall previously, we've gone over rules for transformations of graphs. So for example, you see the x's here. If we're manipulating the x's in some way, this says if we add to the x's, we're going to shift to the left. Subtract from x, we're going to shift to the right. If you see on the outside here, put a number on the outside, this will shift the graph up. If we subtract, we're going to shift the graph down. Recall that if we put a negative sign in front, this will reflect across the x-axis. Put a negative sign in front of x instead, that would reflect across the y-axis. Okay. If this coefficient is greater than 1, then that's going to do a vertical stretch. And if the number is between 0 and 1, that's going to represent a vertical compression. Okay, let's try to look at some examples here, just to give you guys some sort of context. Okay, so we learned recently that the parent function for an exponential function is something of this form. So f of x equals a constant raised to some power. Okay, so let's say we're given that function f of x equals 2 raised to the power of x as a parent function, and we want to describe the transformation of f of x. Okay, so generally what we have here, just to help you guys out, so we have 2 raised to the x plus 3. Okay, so based on the rules that I showed you earlier, the plus 3 is going to indicate a shift to the left. Okay, so this is a horizontal shift, 3 units. I'm just going to abbreviate to the left. Okay, let me go ahead and show you why that's true. Okay, so basically what we can do is, if I were to just pull up Desmos real fast, okay, so if I just pull up, I just put y equals 2 raised to the x, okay, and if I just graph another function, 2 raised to the x plus 3, so as you can see, if I shift if I put shift and 6, I can raise it as an exponent. So if I were to just click on these points here, so as you can see, this says, based on the y-intercept, what you can see here, our y-intercept started at 0, 1. And basically that y-intercept is just shifted 3 units to the left, if you consider the blue graph. Okay, so that is an example of a horizontal shift 3 units to the left. Okay, let's go ahead and look at this one. We have a minus 5 on the outside. Okay, so we can do the same thing if we wanted to. If I just change it into a minus 5, so we're not manipulating the x's this time. So as you can see here, if I compare these, the y-intercept, it's shifted 5 units down. So that's basically what we have here. So this is a vertical shift, 5 units, and then down. Okay. You could do this, you can play around with these as well. So again, well, this would go the opposite way, right? So if we have the x's, so this is going to be a horizontal shift, 9 units to the right, okay? And then this one, well, we're going to manipulate the outside here. So this is going to be a vertical shift. Okay, so this is a vertical shift, 11 units up. Okay, so that's generally what I'm looking for those types of problems. Okay, recall that if we put a negative on the outside here, it's going to reflect it across the x-axis. Okay, so anytime we put a negative in front, let's go ahead and just review that. Okay, so what we have is negative 2x plus 9. So negative 2 raised to the x. So as you can see here, this graph is reflected across the x-axis. If I add 9, then this blue graph should shift 9 units up. So you can see what we have there. It goes here, and it shifts 9 units up. Okay, so if I were just write some of the things that we have here, okay, so this is going to be a reflection. So reflection across the x-axis. Okay, and then a vertical shift. So vertical, I cannot spell today. Vertical shift, 9 units up. Okay, this one looks like this one. So this is just a horizontal shift, 10 units to the right. This one looks like this one here. So this is going to be a vertical shift, 4 units down. And then this, as you can see here, there's a negative sign in front. So this is a reflection across the x-axis. Okay. And then the plus 7 here, this says that this is going to be a horizontal shift. Horizontal shift. 7 units to the left. Okay, so that's generally what I'm looking for those particular examples. Okay, I'm going to show you a few more examples with vertical stretches and compressions, and I'll see you later. Goodbye. Hello. All right, so another thing we also recently learned about exponential functions is that they can be modeled in this shape or form. So fx equals a times b raised to the power of x. So recall that this, you can think of it in the context of the word problem. This was like 1 plus or minus r, depending if we have like exponential growth or exponential decay. So b in this case is going to be the initial value. That's what we start with. And b is going to represent our growth or decay factor, kind of what I showed you earlier with that 1 plus or minus r, our rate. So initial value tells us, can also tell us how much our parent function is vertically stretched or compressed as well. All right. So given this particular function as parent function, we want to describe the transformation of f of x. Okay. So we can do the same thing that we did earlier. Okay. So let's say we put a 6 in front. We have 6 times 2 raised to the power of x. So a little bit hard to see, but basically what's happening is basically this function is being vertically stretched. So if this constant in front is greater than 1, let's say I start off with like 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. As you can see, a little bit hard to see, but it's basically being vertically stretched. Okay, if there's numbers between 0 and 1, like 0.9, 0.8, 7, 6, 5, 4, 3, that function is being vertically compressed. A little bit hard to recognize. The parabolas are a little bit easier, but basically that's what I'm getting at. Okay, so 6 times 2 raised to the x. So this is going to be a vertical stretch by a factor of 6. Okay, this one 0.3, so that's going to go the other way. So I put 0.3, so 0.3, as you can see. So that graph is being vertically compressed instead. Okay, so this is going to represent vertical compression by a factor of 0.3. Okay, 4.7, well, 4.7 is greater than, maybe I'll put that here. 6 is greater than 1. 0.3 is between 0 and 1. So this represents a vertical stretch by a factor of 4.7. So 4.7 is greater than 1. So we're looking at the number on the outside. Okay, and then this number on the outside, this represents a vertical compression. Okay, vertical compression by a factor of 1/8, because that's between 0 and 1. Okay, another question that I see some of you might be asking is like, well, as you can see if you look at the graph here, all of these functions still represent exponential growth. And that's true, because all we're doing is we're just vertically stretching or compressing the graph. Okay, if the number on the inside though, so you see all the numbers on the inside, these 2's, well, 2 is greater than 1. So by default, that's going to represent exponential growth. Okay, but if the number on the inside was something other than 2, if it's greater than 1 growth, but then if it's between 0 and 1, that's going to represent exponential decay. So that's where I see some of you might get a little bit confused, but generally the number on the outside just says if we're representing this by exponential growth or decay. All right, that's basically what I wanted to describe for those problems. Now, let's add another math concept into these problems. Okay, so we're going to add another constant into here, and this constant is called E, which is Euler's number. Okay, E is basically like pi, but E is approximately like 2.718, and it can be treated as a constant, kind of like pi. You know, some years you've learned pi, 3.14159, approximately 3.1416. Let's say I just put it in here. So let's say I just type in E. So that's actually the actual value of E, so 2.718. Now, let's try to figure out in relationship what this means in compared to the graph y equals 2 raised to the x. So, what some of you might see is let's graph 3 raised to the x. Okay, so e raised to the x is basically somewhere between the graph of 2 raised to the x and 3 raised to x. So you see 2 raised to x is in red and 3 raised to x is in green. And then the purple graph is right in the middle here. So you can also represent this. Let's say I put 2.7, let's say I just put 2.718 and I raise that to the power of x. So you can see there, if I just kind of toggle, so that's what e is just basically equal to. E is approximately 2.718. Okay, but it's just another constant, kind of like pi, right? So if you're wondering where this is used in real life, if you're wondering, so I don't have time to teach you guys about these particular formulas, but here are just some examples of where E can be used. So in a future class, you might learn about how to model things with exponential growth and decay, but instead you're going to have this E here. And in the context, some of you may have learned maybe about half-life in chemistry. That's maybe where that you might possibly see E. And then it also relates to logarithms as well. And you'll maybe see that later. It's also used if you wanted to continuously compound interest. So that's where this E is also also used. So there's this idea called like continuously compound interest, and there's like simple interest, and then there's like quarterly, like interest that's compounded quarterly, that kind of thing. But anyway, it's a whole nother topic for another day. But this is just some ideas where E comes from. Okay, but anyway, let's go ahead and look at some particular examples. Okay, so given that fx equals e raised to the x, so e, remember that's just 2.718, about 2.718. So raised to the power of x as a parent function, describe the transformation, okay, of a particular function. So kind of what I showed you earlier kind of follows that similar idea. So remember, if you look what I showed you earlier, so this -3 here is going to indicate a horizontal shift. Oh, I cannot spell today. So horizontal shift 3 units to the right. Okay, if we have a +5 here, this would represent a vertical shift 5 units up. Okay, number 3 and number 4 here, this would be a combination of shifts. Okay, so as you can see here, this +4 and the -6. Okay, so this would represent a horizontal, oh, cannot spell today, horizontal shift, and then 4 units to the left, and then this would be the 6 represents a vertical shift, and then 6 units down. Okay, for letter IV here, this would represent a horizontal shift 2 units to the right, and then this 8 on the outside would represent a vertical shift 8 units down. Okay, so just to give you guys some context, you can also graph these in Desmos. So I forget if I don't think I showed that earlier, but let's say I were to just graph those in Desmos, right? So basically if I have here, so if I have y equals e raised to the x, right? And then the other example was e, so e raised to the x -3. I'm going to put that as exponent. So you can see here, just again, think of e as a constant. It's basically very similar to what I showed you earlier. Okay, so you can see here, this graph, if you look at the y-intercept, it is shifted 3 units to the right. That's how we get that horizontal shift, 3 units to the right. And then if we add 5 on the outside instead, so let's say we were to go ahead and change this up, and then I add 5. So as you can see here, if I look at the particular y-intercepts here, okay, so as you can see, the graph is shifted 5 units up. And that's how we get a vertical shift 5 units up. Okay? So for this one, it's again just a combination of shifts. So this one is going to be a horizontal shift. So horizontal shift, and then 1 unit to the right. And this would represent a vertical shift, 2 units up. Okay? Next, so this one, as you can see, the negative sign in front, that's going to indicate a reflection. Okay? So reflection across the x-axis. Okay? And the 4, remember, since 4 is greater than 1, this would represent a vertical stretch. Okay? Vertical stretch by a factor of 4. Okay? So that's generally what we're doing. And I can actually just prove that to you really fast. Okay? So let's say we start off with our parent function, which is e raised to the power of x. If I put a negative sign in front, flips it over the x-axis. Okay? And then if we put a 4 in the front here, let's say I just create another graph, just so you guys can kind of see it. Okay? So 4 times e, so negative 4 times e raised to the power of x. So as you can see, it's a little bit hard to tell, but it's going to vertically stretch. Okay? If it were like something between 0 and 1, it's like 0.4, that's going to vertically compress. It's just in the opposite direction. So yeah, a little bit hard to visualize, but that's generally how that one would work. Okay? Let's go ahead and look at VII here. So this one would be reflection. So reflection across x-axis, and then the +7 would indicate a horizontal shift, 7 units to the left. Then this one, we have a 2 9s on the outside, so this is going to be represented by a vertical compression by a factor of 2 9s. And then the +10 on the outside, this says this is a horizontal shift, 10 units to the left. Okay? And that's generally what we would do in order to identify the shifts and whatnot. Okay? So please let me know if you have any questions later. Okay? Bye. Hello! Alright, so this is the last part of the video. Okay? So recall that we have an exponential function, so y equals some constant raised to a power. We said that if the constant is greater than 1, then we have exponential growth. Between 0 and 1, that's going to represent exponential decay. So e in this case, e is just a constant that's greater than 1. We said that this is 2.718, as we saw earlier. So that's going to represent exponential growth. Okay, now let's consider what's going to happen if we negate the x. Okay, if we negate the x, recall I briefly showed you guys before that we would create a reflection across the y-axis instead of the x-axis. So let me go ahead and just show you that. So we have y equals e raised to the x. So like I told you earlier, if you put a negative sign in front, this is going to reflect it across the x-axis. But if I take this negative sign out and I put it in front of the x instead, this is going to reflect it across the y-axis. Okay, so that's where this idea comes from. So as you can see here, by reflecting it across the y-axis, what's going to happen instead is this ends up becoming exponential decay. Okay, so let's go ahead and talk about some of the ideas here. So yeah, e raised to negative x is going to represent exponential decay. So in general, if you have something where, e raised to some power, so k times x, where the constant k is positive, so k is greater than 0, that's going to represent exponential growth. But if the constant front is negative, so as you can see is less than 0, that's going to represent exponential decay. All right, so let's try to look at some of these problems. So I purposely put in some numbers here just to kind of throw you off, but really all we're looking at for these problems is just the piece that's in here. So you see here, and here, and here, and here. We're only looking at that part in order to figure out if it's exponential growth or decay. We're not going to worry too much about the number in front. The number in front, all that tells us is it's going to be vertically stretched or vertically compressed by a certain factor. All right, so we want to classify each function as an exponential growth or decay. All right, well, based on what I see here, well, we have we have 5 times e raised to negative 3 times x. So negative 3, well, negative 3 is less than 0, so this is going to represent exponential decay. All right? Then, when we come to this one, when we look at this, well, 8 is greater than 0. That's going to represent exponential growth. Okay. Come down to this one, well, this 5, well, 5 is greater than 0, so that's going to represent exponential growth. Okay. Again, like I mentioned before, all the number in front here, all that says is that's being vertically compressed or stretched a certain way. It's not going to have an impact on the growth or decay. Okay, negative 2 here. Okay, so as you see with the negative 2 there, so this negative 2 is less than 0. That's going to represent exponential decay. Right? Come down to this one, e raised to negative 4x, so same idea. So negative 4 is less than 0, so this is going to represent exponential decay. Right? Similarly, even if I put a 7 in front here, or if I made it 17, it's still going to be exponential decay because we have this negative sign. Okay? This one, so we have a negative sign here, so negative 9 is less than 0. That's going to represent exponential decay. Right? Now we have a positive number. 2 is greater than 0. This is going to represent exponential growth. Okay? And the last one here, 7 is greater than 0. So that's going to represent exponential growth. Okay? That's basically all I'm asking for those particular problems. Okay? Please let me know if you have any questions on anything. And I'll see you later. Bye-bye.